All right, so let us start, and so we start with having a look if we can how we can process things using image J, and I have shared now my screen, and let us see if and how it works. Yes. Oh, okay. I need to click here. But I should be sharing. Okay, I should be sharing my screen, but why doesn't? Okay, and now I think we should take something, some photo from here, and see if we can process this part here. Let's zoom in to 100%, and now let us select here some part. And now we take from here process and fast Fourier transform, and okay, here we are. Here is the fast Fourier transform result, and what I suspect it is, but well, you should actually more look into it if it's correct. But I suspect here we have depicted the complex amplitude of fast Fourier transform as a function of kx and ky. So horizontal axis is kx, wave vector in x direction, and vertical is ky direction. And what we now need to do is to let us calculate the total of all these squared values of all these pixels here inside this. Well, probably it's better to take a circle, not a rectangle, like here. And then study the total sum inside the squares as a function of the size of the square, for instance, something like that. This will help you to check if we have bachelor's law or not. Now, ideally, you would take not inside the square, but you would take two squares, one square here, and another, but I'm not sure if I can draw it now, another square. It seems to me that as soon as I'm drawing another square, this goes away. So the area between two squares, smaller square and 2 times bigger square. And the number, the sum of the squared values of the pixels inside here. Something like that. But it might be easier for you to actually process in scientific Python, CPU. Well, at the end of the day, what you need to have is the sum of the squared values of the fast Fourier transform squared magnitudes. Yeah, so sum of the squared fast Fourier magnitudes over sum over kx's and ky's. So that the length kx square plus ky square is between k and 2k, something like that. I understand that mostly you are still working with it. Please tell me if anyone has finished or obtained some results, right? Or how are you?
I have gotten the same pictures here, but yeah, I haven't integrated yet.
Yeah. So, but if we have this figure here, it's already some progress. What definitely catches the eye here is some high frequency noise, so to say, which I think it's some numerical artifact, which shouldn't be probably here. Like this elongated stripe here along this, and this comes from the you can see it already in this original figure here that there is something going on, some rounding or something. So did you right? I think you tried to work to see what is causing it. Did you make any progress understanding why you have this?
This might be another test of mine, maybe. Yeah, on these that I sent, these are not the newest ones.
Yeah.
Yeah.
You have something better?
I might have.
So yeah. So I can let you share the screen. Maybe if I make you co-host and you want to share screens, and I make you co-host. And but I need to stop sharing. Before I stop sharing, so all the other guys here to so that you understand what I'm speaking about. And now I zoomed in. I can even zoom a little more in here. What I'm speaking here is this like pixelate. What we should have here is like more or less homogeneous slanted darker line and brighter line here, but it's like aliasing artifact seems. You know what is like aliasing, yeah? If you want to put something which is in reality is like a line, but you try to depict in pixels, then you have aliasing is like if it becomes zigzag like here. And so something is not that good in our numerical code, which makes it introduces this aliasing artifact, which is most likely to do with the rounding of the coordinates. And so now I stop my sharing, and if Raido can show some updated results, then that would be nice.
I'm gonna prepare a little, but yeah. So can you see right now?
Yeah, we can see. Yeah. Well, it kind of seems somewhat better, maybe, but there is still some artifacts still in here.
Okay.
So I'm not sure.
So
yeah.
For this one, I already did. I added every time step more the ink or the temperature or whatever.
Okay, you added. Okay, very good. So that's very good. That's very good. But still, yeah, we have still that zigzag still present. And I think if you look here, so there are some places even if you have like a pixel, it becomes dashed line. Like you have dark, and then there is gap, and then again dark, and then again gap. So this maybe okay. Right now we are still not that much in rush, so you can take your time to figure out what is on with the code. Maybe you can fix it. So otherwise the figure looks good, but just it's a question about rounding probably of. So what we do is we calculate a new pixel value as a certain average of the neighboring, which fall into the same cell. So here it seems like something is not exactly correctly done here, or maybe some there might be some conceptual mistake, or there might be some rounding mistake. So first we can look into how the rounding takes place. So there is also possibility to round by modulus or truncate. So like floor function apply. So I suggest we are not doing it right now here, but just to try to look in if you can get rid of that pixelation, then that would be nice. But otherwise, yeah, this figure is very nice here. Looks really nice. But I think some initial features already of that at pixel level, some rounding goes already is seemingly present here.
Yeah, I was just looking where did this.
I just suggest you take your time to if you can do it by next time would be fine. If you still need one more week, it's also fine, because until the end of the semester we have still plenty of time. And with this figure, so like we are not going to do with this code anything else apart. Once we finish with the bachelor checking bachelor's law, that's it. So yeah.
Yeah. Okay. So I'll give you the screen back now.
All right. Now, then we can go again to lecture number 7, and it's your opportunity now to ask what to consider here. So, as a matter of fact, we already discussed some things which were in lecture 7 during the previous lecture, like some that Hurst exponent and super diffusion, subdiffusion, which we discussed to a certain extent during previous lecture, were actually during the previous week actually were in lecture number 7. But yeah, please, your questions.
I would just like to ask that we go over super and subdiffusion.
Yes.
Just
all right. Yeah. So everyone agrees that that's what we discussed. Yes. Yeah. All right. So let me then. Yeah. Because now I need a bright screen in order to have a good quality video. So let us see. So in terms of super and subdiffusion, it's roughly speaking, it's very easy. So what you need to consider is squared displacement, and if this is proportional to certain power of elapsed time, then we say that if alpha equals 1, then let's write it like we have 2h. Let us write in terms of h, 2h. And if h is 1/2, meaning that exponent is 1, then we have diffusion. If h is larger than 1/2, then we have super diffusion. And if h is smaller than 1/2, then we have subdiffusion. Okay. And now let me see if the screen. I think it's right now we can read. Actually, this is simplification in a sense that not anything which goes like power 1/2 is necessarily strictly diffusion, but so for instance, what can go wrong here is that okay, we have x squared goes like t to the power of 2h, but if we take another power, not second power, then what? So like we can consider for instead we can consider x to the power of modulus of x to the power of 2n, let us say, to the power of n, right? To the power of n, and now if we have diffusion, ordinary diffusion, then that would go simply as, okay, if x squared goes t to 2h, then x modulus would go to t to the power of h, right? So we and if we take this and then the power of n, it goes again to the power of n. So it would be t to the power of nh. That's what you expect, and that's exactly what happens if you have diffusion. But on the other hand, if this is not necessarily always the case, that can be actually, and then this is like a water diffusion. But if we have something like x to the power of n is proportional to certain, who knows what power of t, let us write it like psi sub n. So that exponent now depends on n.
Sorry,
and if psi sub n, is not equal to n, then this is not good diffusion. And then sorry. And but now I think things went off screen over there. Yeah. So Kaspar. What do you mean by good diffusion? Well, diffusion. If you take diffusion equation, if you take normal Brownian function, so if you have proper diffusion. Okay, let us substitute good as a real diffusion. Really diffusion. Then other way around. So from here you cannot necessarily conclude that it is really Brownian function, really, but the other way, if this is real diffusion, then that is the case. If you have real diffusion, then x modulus to the power of n goes to t to the power of nh. Well, of course, this is corresponds to h equal 1/2. Now, if we have real fractional diffusion, fractional diffusion, then h might not be 1/2, but it's a range from 0 to 1. One, exclude one. And so what exactly this guy here is a fractional diffusion, real fractional diffusion. This we still need to discuss more specifically, but so not everything which for which nth power, average of nth power of displacement goes as a time to the power of nh is real fractional diffusion. But the other the reverse is true. If you have real fractional diffusion, then this is the case. But on the other hand, there are time series. You can consider as time series x as a function of t. Something works somehow, and then if then you can have situations when you have still power law, x to the power n is still a power law of t, but the exponent itself becomes a nonlinear function of that index n. And now this thing will come into play later on when we are going to discuss structure functions. Well, after maybe after a few lectures at least we'll be having it. So this is described in terms of structure functions, and this actually that psi sub n is called structure function scaling exponent. So this guy here is structure function. And this guy over here is structure function scaling exponent. Structure function scaling exponent. And now the story goes as follows. If structure function scaling exponent is a linear function of h. Now again, I think I need to turn a little bit even lower. So if psi of n is equal to n times h, then you have this happens when you have what is called a Gaussian function. Okay, now let me turn here screen maybe a little to right and make another space to write. So there is a concept of Gaussian function. Gaussian function. F of x. F of t, we will consider a function of t, right? So what does it mean? It means that ft is distributed, or ft minus ft1 minus ft minus f at 0. Ft minus f at 0 is Gaussian, has Gaussian distribution. Has Gaussian okay. Then I say this is Gaussian function. Now, even if it is not exactly Gaussian function, if the distribution tails are not big, or more specifically said, if the second moment of it is finite, so there may be insignificant departure. Departure from Gaussian is insignificant if now second moment of this guy is finite, which means that f of t just a moment before I write to be exactly correct what I'm writing. All right, so before I write this Gaussian function, what does it mean? We have ft minus f0 is horizontal axis ft minus f0, and then you have probability P will be a probability distribution function, and then profile is something like that. Then this is Gauss. But now a departure can be it becomes significant if you have so-called fat tails of this distribution. If it does not go like Gaussian decreases very fast, e to the power of minus x squared. So if it goes exponentially, or if it goes even slower in the power law, then this is a fat tail. Fat tail. And so distribution with fat tails gives departure from is different from Gaussian distribution, and now depending how big, how fat are those tails, it may happen that those fat tails start influencing that structure function. So if in this case, so consider our function f is x, f of t is x of t. So if we take x squared, let us say, if we have Gaussian functions, then dominating part is given by this main part of Gaussian function. But if you have fat tails, so if we start increasing the exponent of x, you want to calculate x to the power of n average, what it is integral of that PDF p times dx multiplied by x to the power of n. So that p becomes multiplied by x to the power of n, and if you have Gaussian function, so yeah, multiplying by x to the power of n slightly raises it, but it's still the very fast Gaussian fall off here on the amplitude dominates. So you never go much beyond of the central regions of the PDF. But if you have fat tail multiplying to, for instance, if it is a power law, then multiplying to x to the power of n might start so that the product p times xn maximum is already starts shifting to rightwards, and so that's why x to the power of n can be much larger than x modulus average to the power of n. So as a result, fat tails then x to the power of n, yeah, put here modulus as well, x to the power of n can be much bigger than x modulus to the power of n for big x. For big x. Because for big N, if you take big N, then they are much bigger. Because x to the power, x modulus to the power of x average of x modulus is something corresponding to this. So this here is around x modulus average. But x to the power of n might be dominated something from here instead. So this here is can be much bigger than that here, so that yeah, and this is if this is the case, if you have fat tails, then we call this intermittent. So these functions are intermittent. Okay, let me not write this here mathematically. Departure, if departure from Gaussian significant, is significant. If we can see from if psi n is now not equal to n times x. If this is no longer a linear function, then I say that you can consider this departure to be significant. So in that sense, the structure function scaling exponent tells you how close is the distribution of that ft minus f naught, how significantly it is non-Gaussian. How strong fat tails do we have? Or simply you can say how intermittent it is. So this guy here reflects you how intermittent is your time series. Now it was like quite a long story from my side, and I guess it is also included into lectures at some with a little bigger order numbers after 7. So it, even so, if it was not now in lecture 7, it will be useful later on. Was it more or less clear what I told you? Yeah. Okay, to sum up once again, so the structure function is quite a simple thing. You have a random quantity x as a function of t, let's say time series x as a function of t, and then you consider nth power of x. Let us say that x at t equal to 0 is, we need to actually here require that x at t equal to 0 is 0. So it starts from origin, right? Because it needs to grow to the power of certain power of t, so it needs to start from 0, right? So if x to the power of n averaged grows as a power law, but the power law exponent is a nonlinear function of that index n. And then we have intermittent time series, a significant intermittent time series. If we have Gaussian time series, then if x to the power 1 goes as a certain power of t, and then x to the power of n goes n times h, where h was like the scaling exponent is if n equals 1. And then this is if we have Gaussian time series. But if you have non-Gaussian time series, the exponent is no longer a linear function of n. And in that case, I describe it in terms of a structure function scaling exponent. And then this exponent itself is a measure of intermittence. The more different it is from linear functions, the more intermittent is the time series. Now, why I was telling all this, it was because I wrote here x to the second power. And then I wrote that is h equals to 1/2, then it is diffusion. But it is not exactly true, because even if h equals to 1/2, it might not be with diffusion, but it is clear diffusion if it is if h equals to 1/2 and we have Gaussian time series. So just let us fix this here now. So that we have on screen as well. Let me check. Yeah, so here h equals 1/2 and Gaussian. So which means that es x to the power n modulus average is proportional to t to the power of n divided by 2. And then it is diffusion. And if h is larger than 1/2, and again we have the same addition that if it is Gaussian, then we have superdiffusion. And if h equal to 1 is smaller than 1/2, and it is Gaussian, then it's subdiffusion. This is if you want to sub and superdiffusion in its strict sense. However, people quite often loosely call also anything, regardless if it's Gaussian or non-Gaussian. If this is bigger than 1/2, then say it is superdiffusion. So loosely speaking, people often don't care about if it's Gaussian or not. Just tell that if the exponent is larger than 1/2, then we have superdiffusion. If it's smaller than 1/2, it is subdiffusion. Also, if you want to be to have exactly in its narrow sense diffusion or subdiffusion or superdiffusion, you need to additionally require it to be Gaussian. All right. Now, this part here, what is on screen, is more or less okay. So everyone. Then there was still a little more talk about superdiffusion and subdiffusion. So the first thing is two things. One is equation which describe, and the other is when it can happen. And so maybe we talk in a reverse order when it can happen, and what are the equations. So let me clean now here. Let me think what we have. And so subdiffusion usually happens when you have traps. You remember the homework which you had at the very beginning. The homework at the very beginning was that you had no, is it shown on the screen? Yeah, it is once. So a cell of vortices. Okay, vortice is going like that. And like that. And then we put here some dye and it starts going along, it moves along separate, some walks, but sometimes it gets trapped into here. Okay. And so in your estimate, you were asked to find how the distance traveled by this particle here depends on the time, right? And what did you find? Do you remember? The result, as a matter of fact, was that x squared grows as e to the power of 1/2. Not as a t, but as a t to the power of 1/2. And this is subdiffusion. Okay. Now, and this is because you have traps, so that particles can spend certain time longer or shorter time here on inside the vortex. So it would be diffusion. It would just walking around the separate. It would be randomly turning at every saddle point. It would turn randomly left or right. Then it would be a random walk with corresponding just to diffusion. But apart from walking, it can get trapped inside here, and it can go out of the trap fast, but that actually it can also spend a long time inside the trap. So because we have traps with power law distribution of waiting time. A power law distribution of waiting time. So usually probability to go out sooner is much bigger than the probability to be trapped here for a long time. And this the probability goes down as a waiting time down. So probability p tau is bigger than, let us say, certain tau naught, is something like in proportion to 1 divided by square root of tau naught, something like that. Is it still on the screen? Yeah, it's still on the screen. Something like that. So we have power law for the waiting time. And such a walk where you have traps with long and short waiting time, and you have power law distribution of waiting times, this is called continuous time random walk. Continuous time random walk, and for that is the abbreviation CTRW. CTRW is abbreviation for continuous time random walk. Now it's already decided in on the screen. Yeah. Now. Maybe I just move the screen to the camera closer so that we can see better. Green writing is not very, but now I think it became readable, right? On the social video. Okay. So continuous time random walk is usually subdiffusion. But you have, you don't need to have such kind of array of vortices, but a simple, like a simple, probably a simple version of it is complex structure. You have like trunk of it, and then teeth connected to it. I think this was also in the original video. This kind of video, right? So you have your input here, like temperature, start heating from here. So heat particles start diffusing, and they can propagate about this trunk here. But if as long as it goes to this, it is trapped. It cannot then move along the trunk. So here teeth work as traps. Here inside of the vortices works as a trap. So they are very similar structures. And in both cases, you have this guy over here. Now, I think in the lecture, we did a certain kind of trick to derive an equation to describe it. Was it? It was terrible.
It was very scary. Some like square roots of like partial.
Yeah. So is everyone afraid of? Did you? So, Raida, how you feel about this? That part, that square root of time derivative.
Oh yeah, I did not understand it very much.
Okay, maybe we take a little time to discuss that. Then, what about it? Yeah. But before we go there, maybe we finish simpler thing. So, so that now we have subdiffusion, which is continuous time random walk with traps. The other thing is that we can have also subdiffusion. And subdiffusion is usually a case when you have Levy flights. Levy flights. So you remember in the case of diffusion, we assumed that all the jumps are more or less the same length. So a random walk, each step of the random walk has the same order of magnitude. But in sometimes this might be not the case. So a good example, just probably a lot of examples, but one classical example is if you track how money coins move. Euro cents, let us say. Yeah, coins. Euro cent. So if you look at your first year, and if you happen to have some coins, usually there are nowadays quite a lot of Spanish and French and who knows what country coins. So now all the coins are quite well mixed all over the euro. But then the question is how they move. And well, if you go to a shop nowadays, people don't use not so much coins anymore, but I guess in EU at least. But it used to be different some times ago. And then you go to shop, and then you give money, and then it cycles inside our country, goes from one shop to other shop. So if you look the motion of the specific coin geographically, or like in geographic coordinates, so it makes random walk just nearby, making steps back and forth, moving from one shop to another, from one person to another, inside the same region. Or something like that. Okay, all right. But then someone takes it and goes and travels to Spain. It's now here. And then it starts doing the same. Okay, this thing here is Levi flight. Long jump. So what you have is now a power law distribution of the probability of the jump lengths. Power law distribution of the jump lengths. So you remember what I wrote before, that waiting time is a power law, probability is a power law of waiting time. Now we have a power law for the jump length. Delta x is bigger than certain delta x naught is proportional to delta x naught. And now longer jumps are less probable, so negative exponent minus something like this. If you have negative exponent here, then roughly speaking, you have Levi flights. Why I say roughly speaking, it is because more specifically you would need to have certain, so alpha shouldn't be too big or too small. So the Levi flights are, I guess, something like from 1 to 2. Alpha from 0 to from 1 to 2. It's correlated from 0 to 1 because I wrote it as correlated. It is from 0 to 1. Now, why is why it is called Levi flight? That's because Guy Levi studied and introduced a new class of stable distributions. Now you mostly have gone through different statistics courses. At least I know guys in here in the rooms, you have had more than one statistics course, right? Right, or you probably also had several, or maybe at least one.
Yeah, at least one.
Yeah, so then you know a thing which is called central limit theorem. So can someone of you summarize what is central limit theorem? Kaspar already started smiling a little bit. Pleasant memories about the statistics course, I guess.
All distributions of intent towards normalism.
Yes, very good. Actually, very good. Yeah, you remember. That's great because that doesn't happen very often. That I ask someone, okay, you had this course, and please tell what was there. Most often you don't remember, but that's already very good result. So yes, central limit theorem states that basically if you have a random quantity x, which has whichever distribution, but the second moment of this is finite, with x square is average is smaller than infinity. And you have certain dp is certain distribution function f of x dx. So p is f is it's a PDF. F is your PDF. Okay. This thing here means that integral of fx squared, the x is more than and if this is the case, and then you take a sum of those random functions. You take a certain sum of xi's. Each of xi has the same f. Each of xi has the same distribution function, but now we have different realizations of that. And you take I from 1 to n. Then this thing here, this distribution function, and this denotes is something like x capital. And then that guy x capital has distribution function f of x capital, which tends to Gaussian. And with second moment of that x capital being equal to original sigma, so it is equal to sigma square variance of that here, the original sigma multiplied by square root of n. Like that. So this is central limit theorem, basically. How do you prove it? Is it on the screen? Yeah, it is. So how you prove it? You take go into Fourier space. You take Fourier transform of, but that's not the point here. We are not going to. Human voice. It means that if you now let me see how we can make transform it to a human voice, giving some example. For instance, if you take dice, it has numbers from 0 to 6. And now if you throw it, then distribution is not Gaussian, because you have equally possible values from 1 to 6. This is no Gaussian distribution, right? If your x is the result of dice throwing, the values are from 0 to 6. But now if you make a very big number of throwing dice and calculate average of it, like 1 million times throw dice and calculate average of it, average score what you obtained after million throwing, then this thing here is almost Gaussian distributed. Average dice score. Average is 1 plus 6 divided by 2, right? It's 3.5, is it? Average is 3.5. So after throwing million of times the dice, you calculate the average score and probability distribution function of that score. Okay, let me write down here also. Dice. 1, 2, 3, 4, 5, 6, equally distributed. Now, this is x equal possible value. X belongs to the set. X belongs to the set. It belongs to the set like that. Okay. Now, x average is 3.5. Now, what is the standard deviation sigma here? Can you also calculate it? Or maybe something. Sigma. Okay, we are not going to calculate exactly, but something, let's write something approximately. So approximately 3.5 maybe to something like 1.51 or somewhere around 1 point something. So 1.3 maybe. But we did not calculate 3, that 3 might be wrong as well. Okay, so some sigma, some standard deviation. And now you calculate 1 million, 10 to 6, n. So, and now you take now our x cap, and here we took some, but it doesn't matter if I divide by n capital as well. So we it just very normalized. So this is now it's almost belongs now for values from 1 to 6. So you cannot obtain larger than 6 and smaller than 1. So it has something now to this interval from 1 to 6. Okay, but now based on central limit theorem, we know that x average, and we know that this is almost Gaussian distribution, with x average equal to still the same 3.5 and standard deviation. It's that 1.3 divided by square root of 1 million, which means that 1.3 times 10 to minus 3. Okay.
So the x average, same as just the sigma in that equation in graph.
Sorry.
So the x average is just sigma in that equation, right?
Yeah, x average. X average, of course. Well, x small average is the average or mathematical expectation of this result. It's 3.5 exactly, right? Because all events are equally probable, you just add them up and divide by 6, and what you obtain is 3.5.
But 1.3 was just what?
We did not calculate this last number, might be wrong, but this is around standard deviation. You know what is standard deviation, right?
So you're basically trying to tell that if you throw the dice 1 million times and you plot it out, it's going to have how it seems to be.
Sorry?
But if you throw the dice 1 million times, then we plot out the values, it's going to have Gaussian to it.
It starts approaching Gaussian distribution. Because we have central limit theorem. Theoretically speaking, you should have been taught why during that course.
Because of like there must be numbers here.
Sorry?
Is it because like there must be numbers here?
No, exactly. How you do it is the way how you derive it, prove it, is that you take your original distribution function PDFs, and then you have a certain convolution integral which describes if you take like sum of 2, let us say, you have convolution integral, but the trick is that if you take Fourier transform, then convolution goes into product. And as a result, if you have sum of n elements, if your random function counted x and its distribution function f of x, then let me move here. So if you have if we have x and it has a distributional function f of x, and now we take Fourier transform f type of now, but x goes then to also wave vector. of k. And then if you take now sum of certain xi's, each of them has say from I equals to 1 to n, then this has, in Fourier space, it has f tile of k to the power of n. The reason why we go to Fourier space is that we can easily calculate the PDF in Fourier space, which just goes to a certain power. And now, whichever function you had initially, whichever shape is, if you take it to a very large power, what starts dominating is only the behavior near the maximum. So if you take to power, a very big power, so everything else which is smaller than the very big value becomes insignificant because you take a very big power. So it's, if you have 2 to the power of million and 2.1 to the power of a million, then 2.1 is much bigger. You can just neglect that 2. So everything else is almost 0 except near the maximum. But near the maximum, you can use Taylor expansion. So near the maximum, this is a parabola. And so it's because you take Fourier transform of PDF to very big number. Then if the number is very big, everything else in the PDF becomes irrelevant except close to the maximum. But close to maximum, you can apply Taylor series. It is a parabola locally, and so this means that this thing here is just corresponding to parabola, and this appears to correspond to Gaussian distribution for this guy in real space. Just like a framework of how it comes, omitting mathematical details. All right, Kaspar, I don't know how you satisfied with the answer, but you can trust me that if you want to have more details, then we will be having a lot more math.
No, it's correct.
Did you get more or less the idea how it goes, roughly?
Well, mathematically, yes. But
intuitively, it's just that. Intuitively, you can just train your intuition that if you have big numbers, it's just going to Gaussian. But yeah, that is why this is called stable distribution. So Gaussian distribution is stable distribution. Gaussian is a stable distribution. And the only stable distribution as long as you have a second moment smaller than infinity. If you have a finite standard deviation, then Gaussian distribution is the only stable distribution. Meaning that if you take a lot of them and sum up, you still have the same distribution. It starts tending to it. Anything starts tending towards it. So Gaussian distribution is the only stable distribution as long as you have finite standard deviation. But if you have infinite standard deviation, then this no longer applies. And then appears a whole class of different stable distributions. And these are the Levy flights, Levy distributions. So Levy distribution is another class of stable distributions. Levy distribution. Levy distribution also stable, but sigma is infinite with infinite variance. Levy distributions are stable distributions, but with infinite variance. And that's why Those flights are called Levy flights because they, at least for long jump lengths, they behave like Levy distribution, follows Levy distribution. Okay.
So if you have infinite standard distribution, then what no longer applies?
Claims that Gaussian distribution is the only state this distribution as long as we have finite variance. If you have infinite variance, then Gaussian, among those distributions which have infinite variance, Gaussian distribution is not the only stable, but there is another whole class of stable distributions which are Levy distributions. So in the class of distribution functions with finite variance, Gaussian distribution is the only stable distribution. But in the class of possibly infinite variance, there is another class of stable distributions, Levy distributions. Yeah, Kaspar?
So, but in reality, we don't have infinite variance.
How you know?
Yeah, well, geometrically on the globe.
Okay, let us see. This is what is another manifestation. Actually, the problem was intermittency. So intermittency, say, is when you the Gaussian no longer applies. So the problem with intermittency is that based on the existing events, you cannot predict what happens in the future because your time interval is just too limited. You have lived something like 20-something years, right? And your life experience is based on those years. And based on what you have seen during that, you cannot extend what happens in the future because you have just limited experience. So you say that something must be necessarily finite, might not be true because you are just your experience is too limited. You have no data about those very rare, possibly very rare events. So let us take, for instance, earthquakes. So you know, magnitude of earthquakes is measured in a Richter scale, which is energy-based scale, so amount of energy released. And roughly speaking, an increase in magnitude by 0.2 corresponds the energy release 2 times bigger. So earthquake with magnitude 8.2 has released 2 times as much as energy as earthquake of magnitude 8. And now, if you look on the available data of earthquakes, then you have the biggest ones are something like, during the whole recorded history, something like 9.5, but only a single one. And like I think it's in Chile, probably, or somewhere Latin America. And then the recent earthquake is the biggest, which was that in the Indonesian tsunami was caused quite recently. That was also quite big, but it was 9 point something, 9.1, 9.2, something like that, I think, if I'm not wrong. And if I remember correctly. And so there are few recorded 9.1, 9.3 in that range, and then you have a lot more in the range between 8 and 9, and so more the smaller you go, the more you have. And now the question is, what about other big earthquakes, the 9.5, and these are a limit? Just it might be because, and most likely it is in a way that the historical data regarding the earthquake is just too limited, so that you cannot extrapolate. And now if you try to calculate the average variance of the earthquake second moment, then that might very well go to infinity. Well, the thing is that, okay, I agree with you if you are saying to me that average magnitude cannot go to infinity. Why it cannot go to infinity? Well, because physically we have well, probably actually second moment also is still limited because we have just Earth itself a finite amount of energy which can be released. But at least based from so there is somewhere far away certain physical limitation, and you need to have cutoff of that power law behavior. So we say that diverging second moment is because of power law in distribution function. So in reality, there is somewhere a cutoff of that power law. That really very big are impossible because of physical limitations, how much energy is over. But this physical limitation is very far from what we have thus far observed. So you can easily go beyond 9.5, some 9.7, maybe 10, something like that. But it just they are so seldom that we have never seen it. And yeah, so if we speak about Levi life and all that, so this goes if we apply to physical phenomena, we should avoid that. Okay, somewhere there is, as a matter of fact, there is upper limit. So mathematically, strictly speaking, they are not infinite, but within the range which we are working, we can consider it the same way as infinite, because we are very far still from the real physically dictated cutoff. All right.
So how much how do we know how far is the cutoff?
For earthquakes, I think you can more or less calculate how much. This depends how much strain energy you can store in the those moving plates. And this is something which you can actually estimate. And people working in seismology might have some idea, but then these estimates are not probably also very precise. But certain estimates can be done here, definitely. So I'm not in no position to say exactly, but what. But that you of course know if you go from earthquake to the volcano eruptions, and the same thing applies of course there as well. And this you probably know that, well, it depends how much you have looked into these things, but there are supposed like Yellowstone National Park is considered to be a very big volcano crater, which erupts very seldomly, but once it erupts, it's something huge and so very catastrophic. So yeah, over there at least the cutoff is very far from what we have seen thus far. So those volcano eruptions which humanity has seen, they are child's play. All right. Now, yeah, so we have Levi flights, and with Levi flights you can have super diffusion usually. So Levi flights, super diffusion. Okay. This is usually how super diffusion comes into play. So a Levi flight is the cause of most often.
In our first homework.
Ah, sorry.
In our first homework.
Yeah.
It's kind of similar to the point example you gave us, where a particle is trapped in some region, and then when it gets like the active region, it can go like very far away. And then
yeah. Yeah.
Very similar to.
Actually not, because if you look how the particle moves, it's like it's still because it has always an opportunity to get trapped. It is not that it makes very big jumps, but it's just that it sometimes gets trapped, and if you have there is interval between trappings, then it just managed to move far. Well, you can consider this and that. You can, in a certain way, you can also consider, of course, such kind of work also as Levy flight, but physically it's more appropriate to consider it as continuum times random walk, because physically underlying you have just some intrinsic moving speed with which it goes, and then it just becomes trapped in this one vortex, in another vortex. So this is a trapping case. But if you consider, for instance, that money motion, then just this time scale, what you usually consider, like 1 day, maybe something like that. So one trading in 1 day. So during one characteristic time scale, what you have in the process, you can show money can just move to the other city very far away if the person goes to plane. And in that case, during one time step, so to say, you can have very big flight, and that this is not the case of trapping. Of course, with money, you can also have some trapping. Some guy just forgets its money into a table drawer, and it remains there. So this is a trapping case. And then at a certain moment, someone finds it, it's again starts using. So in that case, with motion of money, you have both. You have Levy flights, you have trappings. That's what you can also in principle have. And yeah, so quite often there are possibilities of having both. But now, if we start, if you go to description, how to describe it mathematically, then there is quite a significant difference between those two. Well, as a matter of fact, superdiffusion, you could describe superdiffusion also not just as a promotion with trappings, but you could imagine having persistent random walk. We introduced the concept of persistence also during previous lecture, I think. That persistent random walk, let me make some more space. Right here. So persistent random walk if we have a step S. You remember more or less following what we did during the previous lecture, during the very first lecture. So we have SI equals plus minus 1, random step back or forth, and the total displacement X is the sum of those steps. So we can say quantum speed of I equals 1. And then we said that all these steps are uncorrelated from each other. And that's how you obtain random. But now we say that, okay, probability of SI is depends on the value of X. Okay, yeah, SI plus 1. Probability of next step depends on X. And actually not only X, but also previous steps. And now if this probability, if it is biased in such a way that SI is bigger if you had previously made positive steps, then it is persistent. We can write it like that. If autocorrelation function SI multiplied by S I minus N, go back in time by N steps. So this is a correlation function, like not exactly correlation. I have normalized it. We know that have correlation function. We need to normalize, but yes, just autocorrelation function SI times SI minus N. So if they were uncorrelated, then the product would break down into product of average of SI and average of SI minus N, which would give the result 0. But now they are correlated, and if this here is bigger than 0, then it is persistent. And if it is smaller than 1, then it is anti-persistent. And now, if this thing here is a power law of n, then you have you can have a so-called fractional Brownian motion. Sorry? Oh, camera can't see. Yeah, thanks. Yeah, thanks. So if this autocorrelation function is a power law of n, if power law of n, then fractional Brownian function. Fractional Brownian motion. Or multiple function which of ends. Now, and we'll come back again to the that exponent h. So this means that what does it mean? It means that now again I need to think so everything here. So basically, this means that x to the power of x squared average is close to t to the power of 2h. And if it is persistent, h is bigger than 1/2. If it's anti-persistent, it is smaller than 1/2. And that's it for equivalence. H is bigger than 1/2. And anti-persistent is h is smaller than 1/2. So you can have and this recall this is superdiffusion and this is subdiffusion. So fractional Brownian motion itself can be both superdiffusion and subdiffusion. But now why I started talking about traps and Levy flights? This is because in real life you more often than such kind of correlations you have. So from where those come? So in real life, usually superdiffusion, subdiffusion do not come as such kind of correlations, but rather because of those traps and Levy flights. So fractional Brownian motion and like superdiffusion, subdiffusion can be both because of traps and because of Levy flights, or correlations between the steps. And just a physical reality, more often you have because of Levy flights and the traps. All right. And now there was the topic of maybe showing mathematical, heavy math a little, but before going to that, because it's like on the priority list, it is probably not that high. If you have some more important questions, then go ahead and ask. Otherwise, we can go to the math. So
In the last lecture, I think we talked about the 4 dimensions and dimensions of the plane intersecting a plane.
what again?
Like in the last lecture,
Yeah.
something about the 4 dimensions of 2 intersecting.
Oh, yeah.
planes.
Yeah. Codimensions. So you would like me to repeat about codimensions a little?
Just quickly, like, maybe say that first.
Okay.
Again, I understand.
All right. So codimension thing, since we don't think by the way. So codimensions. Let us see. If you have drawings on a whiteboard, which is 2D. Now we take one line, this one. And another line is also 1D. Intersection of them is 1 point. So dimensionality of 1 point is how much? 0. Right. 0. Now codimension, yeah. Okay. Is 2 minus 1 equals 1. And here is the same. So then it's 2 minus 1 equals 1. And now the claim is that codimension of intersection is the sum of those codimensions. So here we know that codium is 1 plus 1 is 2, which means that the dimensionality itself is 2 minus codium is 2 minus 2 equals to the average, as we found it already. Codimension is exactly what it says. So it's codimension. So you have if you think in terms of axes, like coordinate system, one line represents one coordinate x. Then in place, you need to have 2 coordinates. So codimension is in a sense like a number of missing coordinates. So if you have a line in space, you have missing 1 coordinate in y. If you have a line in 3-dimensional space, then the number of missing coordinates is 3 minus 1 is 2. You miss y and z.
So 4 dimension depends on
where you live. Yeah, it depends on where you live. And of course, what happens with intersection is also depends on where you live, because on plane those 2 necessarily intersect, but in 3D usually they won't intersect. It's just very special case when they intersect. Okay, and that's also clear from codimension rule, because in 3D codimension of 1 line is 1, 2 lines is codimension is 2 plus 2 is 4. So codimension is 4, which means dimension itself should be minus 1. Minus 1 is something non-existent, so usually don't have anything. Okay, more or less. Anything else? Then about the fractional derivative. Okay, let us start from the other part. So the question is how to go to obtain what is going to square root of d over dt. What it is. Now, if you want to generalize things, then you will need to have derivative at first sight seems to something which is not easily generalizable to a fraction number, right? But so things become a little different if you go to Fourier spaces, because if you have a function of f of t, and then you take time derivative df of dt, and then take Fourier transform. Then this guy here is I omega and F Fourier transform. That much you remember from mass analysis. Maybe. And also, if you take second derivative, the nth derivative of F, then this equals to I omega to the power of n. Is it more or less okay for you? Kuule, mul on veel veerand tundi loengut. Jah, teeme. Okay, you okay with that? Kaspar is not exactly 100% okay, but now how do you know that this is the case? So very easy. If you take f of t, if it has a f of t is integral of f sine of omega times e I omega t and d omega, right? And now we take here derivative. We take derivative from right hand side and left hand side. And then what happens? Here we have df over dt equals integral. And here, using the, you can put the derivative sign under the integral, but this is independent of t. The only thing which then depends on t is this guy over here. And so you can easily see that this integral now becomes I omega multiplied by f times omega ei omega t. The omega. And now if you look at here, so this becomes clear that this guy here is a new Fourier transform of this thing over here.
Is the F multiplied to omega is like
Index, like Fourier transform. F tile is a function of omega. That's I put. All right. So this now becomes clear, and now it's also clear that you can take whichever number of derivatives you want. Each time you take one I omega t. So it goes like this. It's actually quite easy. All right, and now we have a very easy thing, and from here we can now easily generalize that square root of dt over dt is square root of plus minus, yeah, something like I omega. I forgot to put the Fourier transform sign. Fourier transform. F and Fourier transform of that equal to square root of I omega and Fourier transform. Okay. And now we now Fourier transform that, and you can take reverse Fourier transform, and we obtain expression actually what it is. That's how you can, and not necessarily only square root of time derivative, but any power of time derivative you can take. And what it appears to be is kind of convolution. And now there are slightly different flavors of the fractional derivatives. Let me see if I can show you here. Just a moment. Usually what they use is a so-called Caputo fractional derivative. And just I'm sharing you a screen from Wikipedia. Here you go. So any power, power of the time derivative, the derivative to the power alpha, is expressed in terms of integral. Okay, yeah, we put here we can put here n equal to 1, for instance. And then maybe something easier to read. Okay, there are different versions of it, but the most often used one is Caputo. You can put here different n values. You can, if you put, for instance, n equals to 1, then this becomes fractional derivative of for instance, if alpha equals 1/2, then square root of derivative is 1 divided by gamma function of 1/2, and if derivative of tau divided by square root of t minus tau, then that's what it becomes. Okay, this means that square root of d divided by t of f equals 1 divided by gamma function of 1/2, which is square root of pi or something like that, and integral f derivative at let me write it like that, t minus tau divided by square root of tau d tau. Convolution. Now I stop screen sharing because otherwise on the recording you won't see it. So now what is important here is that this is becomes non-local in time, meaning that value of this derivative at certain moment of time does not only depend on the immediate neighborhood of this given moment of time. If the time derivative of t depends only on the values immediately before and immediately after the given moment of time, right? Do you understand what I'm saying? So you have a certain function f of t, and then it goes like that, and the value of derivative is tangent here. The value of this tangent doesn't care about values here, here, here. It depends only on the very infinitely narrow neighborhood of this given point, which is why we say it is local. It depends only on the local values. Meanwhile, this guy over here depends on the derivative values of far away points. Just that if farther you go, the smaller the contribution becomes because it is divided by square root of tau, but they still remain the contribution to the derivative. So this is here non-local in time. Okay. And now this is exactly what happens if you have continuous time random walk. So a continuous time random walk you can describe, and this was done more or less in the previous lecture somewhat. was that it becomes described by diffusion equation of the type square root of d over dt. How actually, yeah, of n as a concentration is d and a Laplacian of n, something like that. So it is not local in time, but it is local in space. So it doesn't depend on the concentration values very far, only at this point, but it is non-local in time. How we did it, like it was in kind of cheating way we derived during the lecture. It was something like that. Consider the structure with T. And now we try to write here like continuity equation for this certain range over here. That the flux of particles which goes along the trunk equals to the flux, like how much concentration changes here is given by how much comes in, how much goes out, and how much goes to this. And then how much goes in and out, this is described by the usual way. So if we have here, let us say, ordinary diffusion would be described here by, if we had noticed, it would have been dn over dt is d square n over dx square, x is horizontal coordinates. Then the flux J is dn over dx. And the continuity condition, this equation comes as the change at the given point here is dn over dt is just the difference of fluxes in and out. Is dj over dt because of continuity condition. So that's how it comes into play. But now we need to have additional term which describes how much goes over that, and then this becomes depending now on the value of the n at this point here. And then what I would need to know is how much is like J prime flux which goes to here, and then that J prime is J prime is now you might have possibly a little bit different diffusion coefficient into the D. So that would be 7d prime and dn over dy, where y is coordinate to the d. Y. But what you're interested in is only the value of this derivative at this point here. We don't care what is how much flux goes here or here, but since we want to write material balance of the particles along the trunk, then we need to know how much goes at this point here to the dot, and so at the J prime value at this point here. So we want to know the at y equal to 0. That's what we want to know. And then comes the trick that which is cheating to a certain degree, but because we describe along y also in terms of diffusion equation, then we have equation now describing along a single dot as dn over d t equals to that d prime d square n over dy square. Is it, was that also see more or less? Yeah, but then we rewrite it as in operator term. We rewrite it like d over dt minus d prime d square over dy square. and apply to n and all equal to 0. And then we say that if there is, no, let me say, feature something which is easy, more easily seen. So now, if we have a certain operator square root of d over dt, which has a property that if we apply it twice, it becomes ordinary derivative. And this operator here does have this property. That if we apply it twice, it becomes ordinary derivative. If you have such an operator, then you can factorize this operator part here and say that now we have a square root of d over dt minus d prime d over dy multiplied by a square root of d over dt plus d prime d over dy applied to n equal to 0. And now we have options. We have options whether this applied to this is 0, or this applied to this is 0, or maybe this can be decomposed into two parts. One becomes 0 because of this, another becomes 0 because of that. And now what appears actually is that indeed this one here is 0, and that one is not 0, as long as the particles which go into those do not reach the other end. So if we have minus, it corresponds to diffusion from down to up, and if we have plus, it is the other way around. But because particles has not reached here and will not start reflecting back from the end of the tooth, then you are missing that part here. So because the tools are very long, so you can say that actually this one here is 0. So that now the equation becomes square root of d over dt of n equals d prime dn over dy.
Why was the bracket 0?
Because we know that it must be 0, and at the end of the day you must obtain 0. And I was saying that there are different options. It might be that this operator here gives 0, or that operator gives 0, or there might be that n equals to n1 plus n2, so that when this is applied to n1 it is 0, and if that is applied to n2 that is 0. Now what I was telling you that in this case here you have only n1, meaning that this one here applied to that is 0. Just without going to mathematically showing it rigorously, you can do it. You can solve it using again using Laplace transform, no problem. But we are not going to just it's like simplified cheating way of doing it. So I recognize, and you probably also understand that this is a kind of cheating. I'm saying you that okay, this is not 0, this is 0. Here you need to trust me. If you don't trust, make Laplace transform and solve it honestly. And then you have this result over here. And now look what do we need in our equation. We need to have j prime value here at this point here, meaning that this derivative at this point here, right? And this equation here gives us exactly relates time derivative, kind of non-local time derivative, as a fraction of the time derivative at this point here relates to the dn over dy. And now n as a function of t is given along the track. So now we can with this we can get rid of the y coordinate. In order to get a material balance along x-axis, we need to have this j prime over here, which is given by the dn over dy value here at y equal to 0. So now we take this expression and put here y equal to 0, and put here y equal to 0. So in order to have that here, all I need to know is n as a function of t at y equal to 0. So we no longer need y, because I only take y equal to 0 now. And that's how, by plugging in now substituting this here in terms of square root of a dn over dt, you obtain this equation over there. Just like as a rough summary, I think during the previous year it was in more details, like we came to the very end with that, but right now we are already 5 minutes past 5, so probably we should also finish. Just you can also look into the previous lecture, or maybe not, because basically you don't need to. That's not something what I'm requiring from you. What I would like for you to keep in mind is first that if you have traps which can describe eddies, your equation becomes non-local in time, which is described by this kind of equation here, and this here is non-local in time. That's like important part. And here, how you do it, rough sketch here, more detailed in the, during the lecture of the previous year. That should be enough. So, was it helpful additional as compared to the lecture recording?
Yes, but I don't know if this is just my question, but found there to be as a with a derivative of d, but the upper equation there is no derivative.
Why is no derivative of d?
The like
It is like derivative of d, not here.
Oh yeah, right. That's because what goes into here is so that one here basically is the difference of fluxes from left and right. That's why you have Laplacian of n. And what is here is flux into the tools. What we have is d Laplacian n equals to the flux to the tooth, and the flux to the tooth is this thing here, dn over dy, g prime. So this one here equals to g prime, but g prime is that. But this one here, dn over dy, is substituted by square root of d over dt. And so that's how it becomes over here. Now this d is actually what is over here. This is actually not the original d, but certain d star, which appears to be now now the ratio of the original d and that d prime over here. When I substitute, okay, d square n over d x square equal to j prime. Okay. How much is, so this is how much, what is the difference of flux to left and from flux to right, flux from left minus flux to right. This is this thing over here. And this must equal how much flux goes to the tooth. Those as much. But now and now from here, if we plug in the result from there, then we have this thing over here. So j prime equals what? J prime equals d prime dn over dy at y equals to 0. But because of this result over here, this equals square root of d over dt of n at y equals to 0. Okay. J prime, and now I plug this into here, and so this guy here now becomes square root of d over dt of n. And that's the equation what we have.
So J prime is the derivative of J E prime.
Yeah. More or less like that. Maybe some small mistakes here, but like a general approach is like logarithm. It turns out that they still appear to be the same D, but D star is still D. Sim. More or less.
Maybe I'm just slower.
Okay, so this thing here is difference of flux along the track divided by per length, per horizontal length. Flux at here minus flux here minus flux here divided by the distance between them. Now, actually, this like I'm doing it quite sloppily. To do it more correctly, I would you would need to have here like the density of the T's as well, because here right now I assume unit length between the T's. Assuming that unit length between the T's is that if I take density here minus density here, so we have only one to take density here and here minus density flux here minus flux here J and J at x and J at x plus 1. Okay, this minus that is flux to here. And this minus that, if the distance between, if this is unity, then this minus that is second d times second derivative, because J of x is d dn over dx. So this is jx plus 1 minus jx divided by the distance between them is derivative of jx, another derivative. So because it means that this minus that is jx plus 1 minus jx now becomes equal to dj over dx equals to d square j d square n over dx squared. Okay, if the distance between the T's is unit. And now a flux difference is caused by the fact that there is flux into the T, which is J prime. And J prime is diffusion coefficient into the T prime and dn over dy, but taken at y equal to 0, because we lose the flux to the dose at y equal to 0. And we would not like to know that, but we did make a math here before, so that we concluded that this derivative is square root of dt over dt. kuule, veel paar minutit, ma helistan sulle tagasi kohe. Kohe veel, jah. All right. And so, because of this relationship, I can substitute this guy over here, which is flux 22, as his time derivative over here. And so, this difference J plus 1 minus Jx is the second derivative of n over x. On the one hand, on the other hand, it must equal J prime, but J prime is on the one hand related derivative of n over y, but I don't want to introduce y, but I want to keep x only. So I substitute this time the non-local derivative of n at y equals 0 as well as the derivative in time. And I end up with this equation. assuming the distance between these is unity. All right. Now what about homework? All right, so no homeworks in today. Yeah, you need to. Your homework is to just to try to get the code working and finish the bachelor. Now new homework. Now new homework. Work with emphasis on new because you have old homework still outstanding. All right, so see you next time.